Okay, so, whoops, I don't want to do that. Okay, so this is formally section 1, and this won't make a lot of sense right at this moment, but this is kind of the overview of what we want to do. We want to take a data set, and what we want to do is we want to make a picture of that data set. And we're going to make two different types of pictures in a sense, okay? One's going to be a very detailed picture. It's like someone taking a picture of your face really close up. That's going to be the histogram. Notice there's a whole lot of details in here, okay? The other one's going to be kind of like a snapshot of you far away. It's going to give us just a rough idea of what's going on, but it's going to smooth out some of those details. And that's going to be the box plot, okay? So we're going to talk about making histograms. We're going to talk about making box plots. And what's going to happen is, for each of these, we're going to do three things. And so this is kind of an important concept, okay? So for each of these, we're going to have, this box plot, and we're going to have a histogram. And for each of these, we're always going to do the same thing. We're going to make a table of the data for each of these. Then we're going to make the plot. So just like we did with the categorical, we had that table, right? We're going to do the same thing here. How we make this table is going to be different though, okay? So we're going to make a table for the box plot and the histogram. That's going to be the first step. The second step is we're going to make the plots. This will be easy. This part will kind of be a no-brainer. I'm going to step you through this. This is a little more complicated than the histogram, but this should be pretty straightforward. And the last thing we're going to do is we're going to give summary statistics for each of these. And so what is a summary statistic? It's going to be 5 numbers for each of these. We're going to give 5 numbers that are basically going to capture what's in that plot. Okay? So if you were on the elevator with your boss and your boss said, what did that plot look like? You can't describe that, right? So you give these 5 numbers. So for each of these, we're going to specify 5 numbers. They're going to be different numbers. And so those numbers are, in a sense, going to capture what's going on with that graph without you having to look at it visually. Okay? So that's where we're going. Notice this is the same thing we did for the categorical. We made a table, we made a plot, but there really wasn't a lot to report. We just said all you can do is you can tell the mode, the one that's the most likely, but we could give a number here. But it's not as interesting for categorical. So this is what you're going to have to do. This is the important thing. For the exam, you're going to have to be able to make this table, make the plot, and give a summary of statistics. Always those 3 steps. How you do that requires a little bit of understanding. So that's what we're going to talk about today. Okay? So let's see where we're going. Let's look at and so this is just kind of the idea. We want to get a picture, and then we're going to give these 5 numbers, okay? And they're going to be different. I have 4 here. I'm going to put in a 5th one here. It's actually outliers. So you might want to I left this off one year, but actually it's not a bad thing to put in. Well, actually I've left out other things. That's okay. I'll come back to that later. It's not important now. Okay, so histograms. So basically a histogram is very much like a frequency table, okay? With one exception. We're going to plot the number of times the data values occur. We're going to call that number of times the frequency, just like before, how frequent something is, the count. But here's the difference. Notice that when you're dealing with quantitative data, almost every single value is unique. Okay? If I took everybody's height, for example, not a lot of people would have the same height. A few would. So when you plot the data, it doesn't look very interesting. And so what we're going to do is we're going to group the data in bins. We're going to say we don't really care if a person was 71 inches or 72 inches. We want to know if they're between 70 to 75 inches tall. Okay? So we're going to end up grouping these into little bins and count the number of each bins. And then we're just going to plot the frequency. Okay? And what is that going to do? That's going to give us really a pretty detailed picture. Not as detailed as if I plotted every single value, but I don't want to do that. I want to kind of plot the shape of this curve, and in order to do that, I'm going to have to bin these data values. So this, for example, is the plot of the passengers' ages on the Titanic. This is a histogram if I took every year to be a single data point. Okay, and you can see that it's a little too choppy. Okay, I want this thing to kind of resemble a smooth curve. So that's important. The notion that what I really want to be able to do in my mind's eye is try to draw some curve that's smooth. And this has too much detail. So what am I going to do? Well, I'm going to bin them in 10 years. I don't really care if there was someone that was 3 years old on the Titanic, right? 0 to 10 is kind of like a reasonable age range. So I'm going to count the number of people that were from 0 to 10, from 10 to 20. I think here it's probably 0 to 5, 5 to 15, 15 to 25. And I'm just going to plot those frequencies. And now you can see this looks more like a smooth curve. In my mind's eye, I can kind of draw this smooth curve, right? So this is where we're going with this. Now, how do you do this, okay? And I'm not going to get into the details a lot. Let's just look at some data set. This was the exam 1 scores, okay? So here's this whole range, this whole distribution. One thing we're always going to do, and I will try to do this, but I won't promise I'll always do this. We always have to order the data first. Because quantitative has order. When I plot them on the graph, those values are going to be ordered. So you have to make sure first that the data values are ordered. That's always the first step with quantitative. Order the data values. And I've done this here, okay? If there are repetitions, I don't care. I'm just going to put 87 twice. Not a big deal. Now, we have to pick out a bin size. In other words, I need to break this whole thing up into little subintervals. Now, how do I want to do that? First of all, I want the subintervals to be the same width. I mean, it's going to look weird if I have a graph where one bin is real thin and then one bin is real wide. You've never seen that. And you know, you never will. So we want these bins to all be the same size. And normally we're going to pick a nice number. Something that your eye can look at and make sense. So if I bin the data in 5s, 10s, 100s, our eye likes that. If you start to bin the data into like bins of 2.5 or 2.7, a person's just going to get ticked off looking at it. It's too tedious, right? So we're going to bin these things. Usually these are going to be the bin sizes for most of the data we're going to work with. Something nice and even. One thing we have to have, this is a really important condition, is we always need at least 6 bins. When we get to section 2, you'll see why. I'm always going to tell you the bin size because it's a little bit of an art figuring this out. There's actually a formula for this. I'm not going to expect you to know it. It's called the Diaconis-Friedman formula. It tells you the approximate number of bins, but it's a little bit of trial and error. On an exam and a quiz, you don't have time for trial and error. And I'll do it wrong the first time a whole lot. I'll have to go back and redo it. You don't have time for that. So you don't have to worry about this part. I'm always going to give you the bin size. All right? The one thing you really do have to be careful about, though, and this is on you, you have to make sure that you don't count data at the endpoints twice. Let me show you what I mean. So this last comment's really important. And in fact, it's so important, let me put it in red, okay? I'll try to put everything important in red. Okay, let me show you what I mean. So here's the actual data, and I'm going to put this in bins of 5. So I will tell you, use a bin width of 5 and make a histogram. That's all I'll tell you. Notice something. So how am I going to do this? Well, I'm going to look at the smallest data point, which is 0, right? The next one's 43. Hold on. I got a problem, don't I? That should be 2. Let me go ahead and change that. Hold on. Let me go back here. So basically, I'm just counting the number of data values. I think I probably left out the 0. Bring this down a little bit. Okay. So how many data values between, actually I just need another bin, but I'm just going to put them in here. I'm going to say, well, actually I can't do that. Okay, so I actually need another thing here. Let's see. I'm going to have to be kind of careful here. I'm going to put 1 here. Technically, this value is actually equal to, but I'm going to find this here. Okay, so I have 1 data value way down here. How many between 40 and 45? I have 1, right? And I just keep counting like this. You know, I'm just going to take the 0 out of there because it's just too much of a pain. Let me just take the 0 out of the data set. This will make life a lot easier for us. There we go. Okay. And take that out. There we go. Okay. So all I'm doing is I'm just going to count the number of data values. Now notice that there are some data values that fall on the cusp. So this is what I want to draw your attention to. Notice 80, for example, okay? Okay, 80 is actually at the cusp of these two. So you notice that when I define these intervals, I have to make sure that one of them has equals and one of them has less than, okay? And it really doesn't matter how you do it. I could have done this so this was less than or equal to and this was less than. It's arbitrary how you do it. But however you do it, you have to make sure that you can't have a data value in 2 bins. You can't double count data. So if this is less than or equal to, I'm going to use that on every single bin. I'm going to be consistent. And so this is going to be less than. So 80 is going to be counted here. It's not going to be counted there. That's the biggest thing you could screw up in this problem. Okay? That's the biggest problem you can have. Otherwise, it's just like making a frequency bar chart. And so I go ahead and plot this, and I can kind of see what the data looks like now. I might want to have used a little bigger bin to make it a little smoother, but I have a decent idea, right? I noticed that most of the students were up here, but there's kind of a tail coming down here. Okay? So this is the sort of curve that my mind is seeing, something that looks like this. It's kind of skewed. Most of the scores are high, but there are a few people that had low scores. And that's what happened on the exam, by the way. Okay. So I could bin these if I use a little bigger bin size, okay, 10 instead of 5. Now you can see the curve does look a little smoother. I've taken out some of the details, but it looks a little smoother. But again, that's a detail that you're not going to have to worry about. I'm always going to tell you the bin size, so you don't have to worry about that. Okay. Any questions on this part? Good. All right, so what I want to do is I want to talk now about the summary statistics. So first of all, we need to talk about what a statistic is. We haven't even defined what a statistic is, but it's actually an important term. So you can put this at the top of this page. So this will be the definition of statistic. And without putting too fine a point on it, a statistic is anything we compute from the data. It's any number derived from our data set. So what are some examples of statistics, do you think? What would be an example, Taylor, of a statistic? What do we compute from data? But what type? I mean, you look at the grades for this class. What are you interested in besides your own grade? What are you interested in? Anyone want to help her out? What do you think, Jennifer? What do you think is interesting about the data set? What do you want to know? The class, yeah.
Oh, I'm Jessica.
Jessica, I'm sorry.
Okay. I want to know like the averages for the class.
That's right. these are things that you're all very, very familiar with. You could want to know the average. You could want to know the standard deviation. What else might you want to know? What else would be interesting? Suppose you got a 92. What might you want to know?
How many others got a 92?
That's one thing. And you might even want to know, did I have the highest score? Right? You might say, I might have had the highest score. So you might want to know the maximum score. You might want to know the minimum score. Notice, these aren't things that we're computing. That's why I say not to put too fine a point on it. But there's something that we derive from the data. The max, the min, the average, the standard deviation. We're going to see there's actually a lot of things, okay? So here's a statistician's joke. You know, on the 4th of July, when you go out driving, they say, don't drink and drive and become a statistic. Well, you can't become a statistic, okay? You can become a data point, but you can't become a statistic, all right? The statistic is something you have to compute. That's a statistician's joke. Okay, so what is it that we want to compute for a histogram? So you're going to get done, and I'm going to ask you to give me 5 numbers that summarize the histogram. So there's a couple of things we're going to do. We're going to tell how many humps or peaks there are. We're going to call these modes, the number of modes. The most important thing, the thing that your eye really has to go to, is the shape. The shape is really important. It's not obvious that it would be, but it turns out this is a very important property. And then after we get the shape, notice that there's an order, and there's a reason. We do it in this order. Okay, so first we get the number of modes. That's easy. That's low-hanging fruit. Then we get the shape. That's easy. But once we get the shape, then we can determine these 2 things. These depend on the shape. So this is an important point. So notice that there are 2 ways we can compute the center. We're going to talk about what this means. But there are 2 different ways we can compute it. Which one we use is dependent on the shape. There's also 2 different ways we can do the width, and I'm going to add one. This is the interquartile range. I'll come back to this a little bit later. The standard deviation and the interquartile range. We usually don't use that, but I'm going to put this in here. And finally, outliers. Outliers are just what they sound like. When you look at the graph, they're far away from everyone else. They're isolated points. And we're not going to get into a real technical, there's a technical condition for how you determine an outlier. It's just going to be visually. So you're going to write something on the exam like, it looks like the person that was 7 feet 5 inches tall was an outlier. We're not going to make statements for sure, but you're going to pick out guys that are far away. So this is where we're going. This is what we want to do. So let's look at the number of modes. These are really easy. Now, there's a thing about modes you've got to be a little careful on, okay? So let me go back to this picture just to illustrate something real quick. Notice this picture has a lot of peaks, okay? Has a lot of like local maximums, right? There's kind of a point here that's a local maximum. There's one here. If you want to get really, technical, these almost look like maximums too. But how many peaks are there really? I'm going to say even less. Because when I draw that smooth curve in my mind, right? I draw this smooth curve, there's really only going to be one peak. And we kind of saw this when I replotted the data using a different bin size, right? Remember I said it takes a little bit of time to a little bit of trial and error to get the best bin size? Well, here I see correctly the number of nodes when I use the correct bin size. So you have to be careful. We're not looking for little local jaggeds, okay? We're looking for, kind of global peaks, all right? So this thing here, these things here would not be considered local maximum just because there's sampling error, there's deviation, right? So this guy really isn't this low on average. And this smooth curve goes through here. There's only one node. Everybody see that? Anyone have any questions? Because that's a really important point. This is one part you don't want to miss. Okay, this should be easy if you understand that. Okay, so there's only a couple of things you can have. You can have one hump, that's called unimodal, like unicycle, right? One mode. Bimodal, like bicycle, 2 wheels, bimodal. And if there's more than 2 humps, we just say it's multimodal. We don't go into trimodal, quadrimodal, whatever. It's just multimodal. Now there's a reason why we care about this. So this is the interpretation part. This is the part you have to think about. Because what would those two humps represent? Very often, these different humps represent different populations inside a large population. And let me give you an idea of why this is important. So this is kind of a business example. Suppose, for example, you ran a tutoring business, and you want to know where is the peak time that I should be advertising. And so you get this data. This is the number of hours that kids study in school for the SATs. All right? How many humps are there here? There's definitely two. You have to be a little careful. It may not be 100% obvious, but this is going to be bimodal. Sometimes you can't tell. And so I'm not going to be really picky, but here this is definitely bimodal. You can see that there is a definite trend going down. Why would you want to know that? Suppose you compute the average, okay? The average, the center of the data set is going to be here. So you might say, oh well, this is where I need to be offering tutoring. But that's exactly the time you don't want to be offering tutoring. What's going on here? How many times are the SATs offered per year? You guys know this, Daniel.
I have no idea.
You didn't take the SATs?
No, I took the ACT.
Well, how many times are the ACTs? They probably
I took it once and never thought about it ever again.
They're offered twice usually.
Cool.
Okay. So here's the thing. This is when the people are studying for the SAT offered here. This is where the SAT is being offered here. So really, you want to be aware that there's actually two different populations of students studying, and you want to do your advertisement here or here, rather than here. This happens a lot. When you're looking at, for example, gender, if you were looking at strength, you would see two populations for strength, wouldn't you? What would those two populations be, Zach? So suppose I took everyone in BSU and I had them do bench press. Okay? Why would you see two different peaks? Well, let me ask you a question. Do you think that, say, Bethany can bench press as much as you?
No.
What would the two populations be?
Male and female.
Male and female, most likely. There would be a wide distribution. I'm sure there's a lot of females that could out bench press me. There'd be a wide distribution. But we would definitely see two different peaks. Age, you can see two different peaks if you have two different populations. Okay? So this is what you have to be careful about. So if you have different populations, different subpopulations inside a population, you can see those different peaks. All right. So now we have to look at the shape. So this is the key thing. This is the thing we want to be careful about. But it's easy. We're not going to really put a fine point. We're going to say there's three different shapes. It can either be symmetric, or it can have a tail going off to the left. If you remember those test scores, we had that tail for the few people that didn't score really high. We're going to call that left skewed or negatively skewed because the tail is to the left. So these are both skewed. Okay? Skewed means not symmetric. It's kind of like what it means in everyday language, right? If you're hanging a picture and someone says, that's a little skewed, it means it's not nice, it's not even. So the data is more on one side than the other. So these are both skewed. This is left skewed because the tail is going off to the left. This is right skewed because the tail is going off to the right. And that's symmetric. And again, we're not going to put a real fine point. I'm not going to, Sarah Jean asked this question on the quiz about the context, okay? Sometimes you can get really kind of complicated and technical. We're just going to use just kind of a ballpark figure. If it looks more like this than this, it's symmetric. If you can't see a real discernible, definite tail, it's always going to be symmetric. And so why is shape important? Shape's one of the most important things because it's going to determine how we do the other two steps. So if you get this wrong, you're in trouble. The other two steps are going to be off. So what is going on with the center and the width? What are we trying to do? So what we're trying to do with the center of the data, and by the way, I'll just add this real quick. So one thing I'm going to say is that most people think that everything's a bell-shaped curve. Okay? We kind of get this in our mind because you're so used to seeing that everything's bell-shaped. That's totally wrong. When you deal with things associated with human performance, things are not bell-shaped, not at all. So, for example, one of the biggest things that's not bell-shaped is like these things are bell-shaped. But for example, income is not bell-shaped. You've heard of the 95%, right? Everyone goes in the streets and they riot over the 95%. That's what this is due to. But it has nothing to do with inequality. It's just a law of nature. So you shouldn't get too mad at it. And so this was actually discovered. This is a kind of fun aside. This was actually discovered by an Italian economist around the turn of the century. And he was this guy that had this incredible mind. He just thought about everything. And so he grew peas. And one day, as he was picking his peas, he noticed that a really small population of the plants gave the most peas. In other words, not all the plants were equally productive. A really small subset was really, really productive. And he started wondering, is that true for people? And the answer is yes. It's very, very true for people. And so this is called, has anyone ever heard of this? It's called the Pareto principle. Any business or, okay. So this is basically that 80% of productivity comes from 20% of the population. And when you get out and you begin to work, you'll find out that's true. 80% of the work is done by 20% of the workers, okay? So just kind of for fun, this is these are where you see this. So in commerce, if you're in any sort of business, it's a known fact that most of your sales come from a small percentage of your clients. It's not uniform. Not all your clients give you the same amount of business. As a general rule, 80% of the work's done by 20% of the workers. And this is definitely true. Most of the income is held by a very small portion of people. But this is not because the world's unfair. It's just a law of nature. This is how things are. So you can actually see this. If you actually look at the richest 20% of the world, the top fifth, okay, you'll see that they have 82% of the income. It's an actual law. Right? What is the problem today? The problem is that's getting more and more pronounced. So now it's not 80-20. Now it's more like 95-5. It's a little more concerning. But this is going to happen regardless. So socialism and stuff like that, it's probably not going to work. All right. So how does this apply to the data? Okay. Well, the third thing we need to get is we need to get the center of the data. And there's two ways that you can get the center, so you have to be careful here. There is the mean, and there is the median. So let's make a little chart. This is a really useful chart, very simple. So these are how we're going to compute the center and the width of a data set. And this is if it's symmetric or skewed. And what we're going to find out is that if the data set is symmetric, it doesn't matter how we compute the mean, how we compute the center. We can either use the mean or the median. Either one's okay. But what we're going to see is that if it's skewed, we can't use the mean anymore. And that's a little bit of a surprise, because everyone's so used to using the average. They just think that that's the universal best thing to do, and it's not. Here, we have to use the median. And I'll show you why. There's a very good reason why. So you can see, shape is definitely affecting what we're doing. If you guess the shape wrong, you can screw everything up. Now, the simple thing is just to always compute the median, right? Then you can't lose. Okay? So the median works in both cases. So that's the easy thing to do. But if it's symmetric, yeah, you can use either one. And most people tend to use the mean. But you can't use it always. That's the key. Any questions on that? Good. So let's go ahead. We know what the mean is. So if I give you some data set, you just add them all up and divide by the number of data values. That's easy. You guys have done that. So this is not a big deal. The average is the same as the mean, by the way. It's the same thing. Statisticians call it an average. Statisticians call it a mean because there are actually different types of averages. So that would be our answer. Now, the one that's a little harder is the median. And the way we're going to think about median is, think about when you're driving on the road. There's a median in the center of the road. What does that median do? It divides that highway into two equal parts. That's what the median of a data set does. So if we have, so just like a median on a highway kind of splits the road into two equal parts, the median splits the data set into two equal parts. So the median we can think of as the middle data value. Technically it's the 50th percentile. We're not going to worry about that. We're not going to get too much into that. And so if we look at these test scores, okay, we have 32 test scores. So what's going to be the middle data value? Notice I have to have the data values ordered. So would you say this is the middle data value right here? I wouldn't. There's actually 16 in both rows. So it's a little tricky. We don't actually have a value that's right in the middle, do we? This is the 16th, and this is the 17th. And the answer is somewhere in between there. You can pick any number, but what's the most reasonable number? What do you think we should do, Brendan?
80.5.
What's that?
Wait, what's supposed to be?
Okay, so here I have in a sense two middle values, right? That's the 16th data value, that's the 17th data value. So the middle one's going to be right in the middle, right? Actually, the middle of the data set is between these two, so we're going to take the average. So the median here is going to be 80.5 for this data set. Let me show you a few examples. So first of all, when you compute the median, the most important thing you always have to do, the first thing always, order the data. Make sure it's ordered. Devious me, I might not have them ordered. So we have to order the data values. Now notice, if you think about it carefully, you realize there's actually two different cases. There's a case when you can have an odd number of data values and a case when you can have an even. So let's look at the case where you have an odd. So here I've ordered the data values. I have 1, 2, 3, 4, 5, 6, 7. So I actually have a middle data value. So when I have an odd number of data values, I'm always going to have a data value that's a median. So the median is 76 there. So the median is a data value here. That part's easy. So what if we have an even number? Well, how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They're ordered. So these are the two middle data values, the 6th and the 7th. Okay? So I'm going to take the average here. The median is going to be 84.5. So it's pretty straightforward. It's just intuitively what it seems like. Notice this 84.5, it literally split the data set into two parts, an upper part and a lower part. And there always has to be the same number of data values on both sides of the median. Notice there's 3 here, there's 3 here. There's 6 here, and there's 6 there. It does just like the median in a row does. It splits it exactly in half. Okay, questions on this? And we'll do some more problems on this. So that's really all. That's all we need for the center. Now, why do we care? Okay, so this is a little bit of an aside, but it's important. Let's look at two different data sets. Notice this data set is symmetric. This is the plot. you can see that it's symmetric about 5, right? 3 and 7 are both 2 away. 1 and 9 are both 4 away. So this is a nice symmetric data set. If you compute the mean, if you add all these things up and divide by the number of data values, you'll get 5 here. So the mean here is actually 5. Well, what about the median? Well, how many data values do we have? That's the first thing we have to do, count. First we have to check, are they ordered? They're ordered. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Odd number. So the fifth one will be the median. 1, 2, 3, 4, 5. And it just happens the fifth data value is 5. That won't always happen. But this is going to be the median. So the median is also 5. And that's really what we said. Whoops. And notice this is exactly what we said before. We said that when the data set is symmetric, these two things are basically the same. They're usually not exactly the same, but they're really close. Close enough that we can use either one. And of course, I set this up cold-bloodedly, so they were exactly the same. But notice that that might not be the case if the data is really skewed. So let me kind of give you an example of when this would happen. Suppose, for example, I'm a really mean business owner, and I have 5 workers. I'm going to pay them each $1, and I'm going to $1 an hour. I'm going to pay myself $999. My business is doing fine, but this is what the income distribution is going to look like. Okay. Or if you want, you can make these thousands of dollars. It doesn't really matter, okay? So notice that there's a whole lot of people who aren't getting paid very much, and one person is getting paid a lot. This happens, by the way, with companies. If you look at Google's, the distribution of pay, it actually looks something like this, because the guys who are the CEOs make so much more money. Now, why would we care about this? Well, let's compute the mean and the median. Which one's easy to do here? Which one's like a slam dunk? What do you think's the easy one? The mean or the median?
The median.
Median, that's right. Because I have so many ones, right? I already know what the answer is. Let's verify. We've got 1, 2, 3, 4, 5, 6. So it's going to be between these two values, right? The third and the fourth, 1. The median's 1. What about the mean? Well, we have to do a little bit of work to get the mean, right? So the mean here is equal to, and I have 5 ones, so rather than write 1 plus 1 plus 1, I'm just going to write 5 plus 999 divided by 6. And when you do that, it ends up being 167.33. And the median was 1. Now, what could happen? So you hear this thing a lot. People say that statistics don't lie, but liars use statistics. Suppose there's a news company that gets a hold of my records. And they report, this guy, he's so terrible. He pays his workers so low, and he's just the worst in the world. And I come on TV and say, no, guys, you got it all wrong. The average salary is 167. I don't know where they got that number 1 from. Now I look like a great guy. So what number I choose to be representative of the center really affects how people think about the data. Here, people think I'm a great business owner if I use the average, but if we use the median, I don't look so good anymore. And I really should be using the median. That's why I'm using the median here. The median is really representative of what people are getting paid, not the average. The average is out here. So that's why we have to be careful which one we use when we have skewed data. Because the mean and the median won't be the same. They'll give very different interpretations of what's going on with the data. Let me give you a few historical examples about this. So, and here's basically what's going on. I'm not going to make a big deal of this, But what's happening is the mean's getting pulled out towards the tail, because notice what you're doing is when you're adding that huge value, okay, it's skewing the mean. It's pushing the mean out towards the tail, because this value is so extreme. So whenever you have a distribution that's skewed, the mean is always more towards the tail. And it's not going to be the same as the median. Whereas when you have a nice symmetric distribution, these are exactly the same. And you can see the same thing's going on here when you have a tail like this. The mean is getting pulled out towards that tail. So again, we have to be careful, because they're not the same value. They can give a very, very misleading representation of what's going on. I'll show you an example historically that actually happened. So this is real life. When free agency happened in baseball, the salaries went up a whole lot. Who here knows who Scott Boras is? Probably the guys all do. He's like this mega great sports agent. The way he got his reputation was, when free agency first happened, these are the different salaries. Okay, this is the average salary that's in green here. This is the minimum salary. Notice that before free agency happened, there wasn't a lot of disparity in the incomes. They were all pretty low. Everyone was pretty well grouped together. Then all of a sudden, when free agency took off, the salaries started to go up. Okay, and this is when Scott Boras started kind of negotiating. And here's what happened. So this is what the actual baseball salaries looked like in 1994. Notice it's highly skewed. This is the sort of thing you'll see on an exam. There's no doubt about this, okay? It has one maximum, it's unimodal, and it's right skewed. But here's what he did. This is the median, and this is the mean. And so when he negotiated for his clients, he said, well, my client's about an average player, and the average is over 1,200,000 and change, so that's what he should get. And the business owners, even though they're smart guys, they didn't really realize what was going on. They said, okay, fine, we'll give your guy $1,200,000. This went on for about 2 years. They didn't realize that the real value was the median. And then when he did it like the second or third year, the owner said, you know what, you're right, your player is about an average player, and the actual center of the data is not the mean. It's actually the median. So he's going to get $500,000 instead. So this is what happened with negotiations. This number is twice as big as this one. So it made a huge difference. So for a while he got away with it, and that's one of the reasons why he has this great image of being as this super negotiator, because he kind of took advantage of this. But this happens to you. For example, when you get out and you start to own property, there's going to be two values that you have to worry about. First of all, when you go to sell your house, when you actually go to buy a house, you'll notice the house prices look really high. And you kind of want that. Even though you don't want to pay a lot of money, you want to be in a nice area. So a lot of times the realtors, they'll kind of inflate the price. But when you go to pay property tax, you don't want your property evaluated at that same value that you paid for it. So here, when you're buying the house, okay, in an area, the realtor might tell you the mean, because it makes you look like you're getting a bargain, and you're in a nice neighborhood. But when you go to pay property tax, you'd want to pay on the median, because it's lower for a skewed distribution, and house prices are definitely skewed. Okay, so this is kind of what's going on, and why we care about which one we actually use. Questions on this? Okay, so let's go ahead and look at the width now. So this is everything we have to know for the center. And just like I said before, the mean's getting pulled out here. Okay. So the last thing we want to look at is the center. There's two different measures for the center. We're going to talk about the standard deviation and the inner quartile range. And these are, in a sense, kind of measuring the average distance of the data value from the mean, in a way. This is, I'm not going to spend a great deal of time on this, but this is the formula for the standard deviation. This is in the book if you want to go through it a little bit more. But essentially all we have to do is we're going to compute the mean from the data set. We're going to take the difference, This is where the deviation's coming in. The deviation is a difference from each data point to the mean. We're going to square those, and then we're going to add them up and divide by the number of data points minus 1. Take the square root. It's a nasty looking formula. Nobody likes it. But this is the standard deviation. And I'll go through some examples. It's not hard to do. There are some little things you have to be careful about. So let's look at a good example. This is looking at two different pictures, and this is their ERA. And so let's go ahead and compute the mean and the standard deviation for each of these. So if we compute the mean for Roy Halladay, I'm going to leave this up. So we're going to put the mean, and we're going to put the standard deviation here for each of these. And although I expect you to use the formula, I'm going to cheat and use my built-in calculator function just to save some time. So we're going to add 3.19 to 3.71. 2.78 to 2.79 to 2.44. So if you add all these numbers up and you divide by 5, we're going to get 3.12 for the mean. And I'll leave it as an exercise for you to compute the standard deviation by hand, but it happens to be 0.438. I'm going to round that to 0.44. The units are earned run average. Okay, so those are his numbers, fine. Let's look at this Hernandez, okay? So let's compare him to Hernandez. Same thing, I'm going to add all these numbers up. So we add up 4.52. Oh, hold on, I got to clear this. Okay, so we add 4.52 to 3.92 to 3.45. 2.49 and 2.27. And when you do that, this mean is going to be 3.33. So you look at these guys, there's not a huge difference. You might think, oh, they're about the same quality of picture. But let's look at the standard deviation. Standard deviation here is 0.95. Yes?
Do we have the standard deviation formula in here, or is it?
It's in the book,
Okay.
and you can follow the instructions. When I do the key, I'll put it in there explicitly, but it is in the book. And I assume you guys have kind of computed standard deviation before. Anyone that never computed a standard deviation ever? Okay. I'll put the formula up. Okay, now notice that we have the mean, we have the standard deviation. So this kind of goes to the question of why do we care about the width? Their averages are about the same. Are they the same sort of picture? Well, this standard deviation is telling us something. It's a measure of how wide the distribution is. It's a measure of how variable this person's performance is. Okay? So this is kind of the idea here. And let me show you why we care about the standard deviation. Why we care about how wide the data points are. So this is kind of a hypothetical. We'll do this little story and then I'll end, okay? So suppose you have two snipers, okay? Say Andy and Bill, all right? And Andy is going around, he's saying Bill's not a good sniper, he couldn't take out a cow from 5 feet away, he's terrible. And they decide to have this contest, okay? So they're shooting at these little ducks. You've seen these like in carnivals, right? The duck goes along, and what we're going to care about is how far to the right or left they are when they try to hit the target. So they're going to shoot at these little ducks as they're moving, and we're going to be interested in how far they are off from the target. And so let's go ahead and suppose we look at Bill's. That's what he looks like, and then we look at Andy's. Now, who's the better sniper? Who would you want to hire if you were going to take out somebody? I'd want to hire Andy. He's almost always going to hit the target, and Bill's way off. He can hit anything, right? So there's no doubt that Bill's a better sniper. You can look at this and see this. But here's how statistics can fool us. Let's look at their actual distribution. Okay, so here's their mean. Notice that Bill has a mean of 0. Andy's mean's not 0. So Andy could go around saying, hey, I'm the better sniper. We had this contest, and here's the average I was off from the target. 0. And this guy's off 0.3 inches, so you definitely want to hire me. But it's very misleading because the width are very different. This person is not exactly at 0, but the values are very closely grouped. The standard deviation is a measure of the width. Okay? When you compute the standard deviation for these, I didn't put it on here. I don't remember what they are right offhand. But this standard deviation is very small. So this number is very representative of what you're going to get because there's not a lot of width in that distribution, right? The values are all very, very tightly clustered around here. Whereas this guy, the average is 0, but it's very, very wide. So the standard deviation tells us how representative this number is of the whole population. When the standard deviation's huge, the distribution's wide. That's Andy. 0 is not representative of the average performance. Okay. But when the standard deviation is very small, the values are tightly clustered, then the mean is a really good measure of what you're going to get on average. So this is why we care about the mean and the standard deviation. Okay, let me hand back the exams. This will be it for today. We'll do box plots. I'm not going to give out any homework right now. I'll send out homework, but we don't have to worry until the end of the second exam. I mean, the end of next class. I don't know why I'm thinking about the second exam. Okay.